Thank you very much, Rafael, for the introduction and for chairing the session. Right. So let me start. I feel that I'm giving a presentation in an area which is not really my own area or my major area of research. I've been working mainly on mixed integer programming applied to transportation logistics. And I happen to work on what I'm going to present today because I think the typical two touching areas of traffic and transportation are getting closer and closer, and especially routing is one of the areas where which involved in the past mainly freight and not people, and instead more recently I think it is involving people too. So my major areas of research, because these are the areas where I have been working in the last years. I think one is car and ride sharing, although these days sharing is not very popular. It was before the virus, and hopefully we will come back to that, because there's a way to really reduce the environmental impact of transportation, and it has been a very important area and still is, I think. On-demand services, flexible itineraries for all kinds of transportation. This is another important direction, and route guidance. This is where I am today. So I'm talking about this kind of topic. So the starting point, you see on the left, the University of Brescia. For those of you who have not been in the north of Italy, especially in Brescia, which is on the way to Venice from Milano. And you see in blue on the right, the Lake of Garda, which is a beautiful lake. So if you have to travel from Brescia to the lake, to Sirmione in particular, you have different ways. The fastest one is to go through the highway, which is the gray, and it is the shortest path, 53 minutes this time of the day. And that highway is usually often very busy, and you may get stuck in traffic and congestion. And as it happens in many ways, in many situations, Google Maps rather than Waze or other systems offer you alternatives. So when you ask your satnav or any of these systems, which is the shortest path, the systems give you the shortest path. In this case, it's 53 minutes, depending on whether you ask the time or the distance, it gives you the shortest path. But it happens that now also alternatives are given to you. In this case here, you have the second best, 1 hour and 7 minutes, 55 kilometers. And why? Because it is longer in distance and in time, so it is dominated. We're not interested in such a path. The problem is that when you start from Brescia and you're looking at the shortest path, the traffic conditions are of a certain kind, and along the way, the traffic may change and you may get stuck in traffic, and the time to destination may change with respect to what was expected when you left the origin. So basically, when another path is offered, it is because there is a lot of uncertainty, and the system does not feel confident enough to say, please go on the shortest path. because maybe this will not turn out to be really the shortest. So the point I want to make here is that traffic has an impact, and also if there are many living from Brescia to the lake, it could be a good idea to distribute them over different paths and not to send them all on the same path, because the shortest path for one may end up to be a congested path for many. Until few years ago, we only had information about the shortest path, and all the satnavs were based on time, expected time, estimated time, and distance, and you could choose one of the two criteria, and that was it. Now more and more information is available on the traffic. For example, here you see the area of Milano, and you see in orange, red, green the different levels of congestion, and the time to traverse Milano is really highly variable. You never know in advance if it will take time X or time twice X or 3 times X or whatever. And also it's very difficult to decide the path, because even though we have these systems, still you don't know what the others will do. So you know what you want to do, where you want to go, but your decision is really the quality of the decision that you take depends on the decisions of the others, right? It is not, your decision is not independent of the behavior of the others. So whatever the situation of your trip is, outside an urban area or inside an urban area, especially in north of Italy and in Lombardy, where the density of the population is very high, you find congestion in town and outside of town. So in any case, you may end up spending a lot of time along the path, and often the time is really high, and higher than you expected, maybe also. So the simplest satnav gives you still the shortest path based on the map and on your origin and destination. In some cases, as the first example that I gave you, it gives you 2-3 alternative paths, the shortest and the second and third shortest in time, on the basis of a map of the traffic and of your origin and destination. So my question here, I want to ask you, and I ask myself, if it is time to think about a new generation of satnavs, which coordinate basically their decisions with the others. So where each is not independent of the others, and of course this may be a sort of something far from application. But autonomous vehicles and connected vehicles make this kind of a dream more realistic than it was until a few years ago. So user equilibrium, system optimum, we know very well. With user equilibrium, we know it is based on selfish behavior, what we do, basically. So we choose our shortest path, and if we hear that there is a better path the day after, we will move, and then at the equilibrium we will we will, same origin, same destination, spend the same amount of time from origin to destination. And we know that the total travel time may be higher than expected on the network, because in the system optimum, we may have a minimum total travel time over the network for all origins and all destinations. But of course, we also know that some drivers may have to travel along very long paths. So what I'm going to present is a compromise between these two, which is the result of a coordination of the decisions on the paths. So the idea is to try to reduce this price of anarchy. So the goal is to find a traffic assignment with controlled, limited inconvenience or unfairness and reduce the price of anarchy. This is the idea. And the first paper dates back to 2005, and that was our starting point. So the idea is that we do not want to have given different users, different travelers from same origin, same destination. We don't want to have very different traveling times. Although in the future we may have autonomous vehicles, and they may be more willing to accept to travel along a path which is not the shortest. Still, the unfairness, the difference between the paths may be something that is not acceptable for several reasons, also because of the time that also autonomous vehicles may not be willing to spend. So what is the maximum allowed inconvenience? Well, it is the percentage of which the path is longer than the shortest path. So if we have an origin and its destination, the black arrow shows the shortest path, and we may have the blue path, which is slightly longer, and then the red path, which is a bit longer. But the red path is not longer than the black path by 5%. So there is a maximum. There is a limit on the difference in length between the shortest path and the path that we consider to be eligible. And we might think of distributing the flow over the different paths. So 50% of the vehicles may go on the shortest path, and 35% on the second shortest, and 15% on another path. This is the picture.
Oh, sorry, let me just quickly interrupt. There's a question from Samisa. Even with solving for constrained SO, who decides which vehicle gets the slower route? Would it be random?
Yeah, that is an open question. At the end, I was mentioning a few open issues, and this is an issue, how to distribute. I think that it is everything. There is an open. It is an open area for research, I think, and there are different questions. One is the incentives. Do we want to give incentives? Also in urban areas. Now, if you think about how things work with congestion charge, right? Which is a very, very naive system to control the traffic in urban areas. If you could coordinate the decisions and give incentives to some cars to take a longer path, maybe we would really end up with a better global situation and even fair situation with Also the traffic. The traffic has an impact at the moment on some parts of the population. Those who live along the most congested roads. So there are many issues here that are relevant. But yeah, I'm not facing any of these. I'm just presenting the models, and I'm trying to convince you that it is possible to reach a compromise between the user equilibrium and the system optimum without increasing the unfairness too much. With a small amount of unfairness, we may reach a good compromise. This is just the message of my talk, and all the rest has to come, if it will come.
Samita says thank you.
Thank you, Samita. There was another question, Raphael? No.
No, it was just that one question. Right.
So this is the paper by these German colleagues. It received an award. It appeared on Operations Research in 2005, and they presented the first model of this kind, which is called constrained system optimum approach. Well, this is a travel time on an arc with the flow which is xij, and the model that presented is nonlinear and has an exponential number of variables because you have an exponential number of paths that you have to consider. Even if you limit the unfairness, still the number of paths may be huge in real networks. So nonlinear is not good, exponential is not good. So this was the starting point of our work, and this is what we did. We started sort of as an experiment. I remember I contacted, I was contacted by Valentina Morandi, who was a PhD student of mine, and I told her, look, this is a new area for me. I'm not sure where we will end up. Up to you. You can work on a routing problem, and I feel very confident there. We can publish papers quite easily. Here, I'm not sure, but I think it is interesting. And she accepted the challenge. And the work I carried out, you see here names from my research group in Brescia, and also Martin Salvasberg from Georgia Tech joined me in this adventure. So first of all, the concept of inconvenience or unfairness. There are different ways to define the unfairness, because we want to find the traffic assignment. So we don't have the traffic on the road. We have to find it. So the loaded inconvenience, for example, you could measure given the traffic. But since you are building the assignment, you don't have the congestion, you don't have the traffic on the network. You have the normal inconvenience and the user equilibrium inconvenience. And we used this measure to measure the inconvenience of a path. So it is the user equilibrium inconvenience is the ratio of the experienced travel time with respect to the travel time in a user equilibrium. And then the very first paper we published, which I mentioned earlier, was a very simple model. And in fact, I think the ones I'm going to present are better. This is very simple. It is just the linearized version of the one presented by Jan et al. In Operations Research in 2005. And here we just plainly minimize the total travel time, given that the flow is distributed over the eligible paths. That is, the paths that are not longer than the shortest path by the maximum allowed inconvenience. And so the idea is very, very simple. We linearize the objective function, which is nonlinear. So this is a piecewise approximation of the travel time. And the upper part of this formulation is just to describe the piecewise linear approximation, and then this the a figure to show that the piecewise linear approximation is very, very close to the real function. Here we have 1,000 pieces, and we made several experiments of trying to approximate the function, and basically this works very well. And for the experiments that we performed, there was no computational problem. When you have linear models, things are very simple, and the software that we have available today is really working so well. So it is not a problem, and also we saw that with 100 instead of 1,000 as a level for the approximation, things work very well, and you don't gain much by raising this number above 100. Still we have the exponential number of paths, because we have made the nonlinear function linear, and that's fine. Still we have the exponential number of paths. So we developed a heuristic column generation for reducing the amount of paths that we generate, and the idea is simply to generate an initial number of paths, eligible paths, and then we solve the problem, the linear program restricted to these paths, and then we build a network and we find new paths, and we continue until we sort of converge. We generate instances. In fact, we have a generator of instances of different structure. This is a typical instance inspired by Italian cities with the city center and rings around the city center with different capacity, and also this generator allows us to generate different kinds of city structures. We used as a basis for the experiments 40 instances with 150 nodes, 8 instances with about 300 nodes, and then we used these four instances that are taken from the literature, from the web. And these are the size that you probably know of these instances. And still, also for these instances, there is no computational problem with the linear approximation of the nonlinear function. So, well, I'm in optimization, and so my first worry is how good the heuristic is. So we test the heuristic, and these are the errors. So the heuristic works well. So good. This is a good starting point. So both the average gap with respect to the optimal solution and the maximum error are very low. So this is good. Of course, we made these experiments on the 40 instances of smaller size, 150 nodes, and for those size we can find the optimal solution, and then we could compute the real error. You see here two columns called SBGen and DualGen, because we had two heuristics. In one case, we generated a new improving paths based on a search for shortest path on a network. And in the second case, we used the value of the dual variables associated to paths that are not yet included. But in any case, the idea is the one I described earlier. And then here I want to show you by how much we reduce the number of paths through the heuristic. You see here in the top line, the line that the row that starts with n equal to 1000, you see the total number of paths. So if the inconvenience is 0, it means that all the flow will be sent on the shortest path. And there we have in total 1,170 paths, because we have 1,170 OD pairs. If the inconvenience is 5%, the total number of paths increases to 17,000. If the inconvenience is 10%, the total paths are 45,000, 50%, 93,000. And the number of paths we generate is instead 1,170, 1,540, 1,590. So basically, the number of paths that we generate is very, very low with respect to the total. So it means the heuristic works very well, is very efficient, and it guarantees a very good performance in terms of error. Here is the result in terms of user equilibrium and system optimum. So on the bottom, we have you have the system optimum total time. Here, this is the line for the system optimum total travel time. Here is the user equilibrium, and this line indicates the total travel time with the linearized model that I showed. And if the inconvenience, the gamma value, the maximum inconvenience is, you see, 2, 3%, 4%, we are between the system optimum and the user equilibrium, and it goes down rapidly to the system optimum total travel time. So we converge quickly to the system optimum with a level of the maximum inconvenience, which is relatively small. And also, I'm not showing today the different statistics that we obtained, but you can see also that the number of cars or the flow that travels on paths of the maximum inconvenience is very limited. So very few cars are really have to pay the price of the maximum inconvenience that we set. We also made experiments to see the impact of compliance if 100% of the cars follow sort of the path that we indicate, and if this alpha is, for example, 50%, it means that 50% will travel on the path that we indicate, and 50% will travel on the shortest path. Right? They will not follow our indication, and also here you see that still the total travel time drops very rapidly. Again, with an inconvenience which is relatively small, drops to the system optimum value, close to. Here I'm presenting a slightly, maybe not slightly, a different objective. So in the paper by my German colleagues and our own paper, the one I just mentioned, we have as an objective the total travel time, right? The problem when you minimize the total travel time is that you really put together travel times of very different nature. And you may not be interested in all these travel times. I mean, what we really care is the congestion. We don't care about the parts of the network which work nicely, right? Usually the congestion takes place only on some arcs. So what we really care is about the average congestion on the most congested arcs. So here we change the objective. I don't know if you are familiar with the CVAR function, conditional value at risk. It comes from finance, but it has a meaning in different kinds of context. And here I think it does. So here we take as an objective the average arc congestion or the average travel time on a percentage of the most congested arcs. So if the percentage is 100%, we are back to the same objective function. If the percentage is 1%, we just concentrate the attention on the 1% of the most congested arcs. The mathematical programming formulation changes, but still the model remains linear, which is really a good thing. And I'm not going into the details of the formulation, but the idea is that the objective function has changed. And here you see what changes when we change the value of the percentage of the arcs on which we concentrate. So if beta is 1, here we take the average over all the arcs, and moving up, we reduce the percentage of the arcs on which we concentrate, and of course the total travel time increases. The smaller the value of beta is, the higher the average congestion is, because we concentrate on a smaller percentage of the most congested arcs. But what is interesting to note is that, again, the total travel time, even on the most congested arcs, and only on the most congested arcs, drops to the value of close to the minimum that we obtain with the system optimum.
Samita has a question, one more question. Did you consider travel time over free flow travel time as an alternative?
The user equilibrium, what do you mean, Samita?
I'm going to find Samita and ask. There we go. I'm going to ask you to unmute.
Okay, thanks, Rafi. So I was wondering, so if you take about this, since you're like you said, you want to now try to capture the part that is above the congestion causing components of the routes, right? So you could take the free flow travel time, forget about user equilibrium, just the travel time if there was no congestion on the road link. Let's say that's some baseline travel time, and only penalize for the travel time that incurs beyond that. So if on a link it took 2 minutes and now it takes 3 minutes, you only penalize that 1 minute additional travel time.
That's the total travel time.
Total travel time minus the free flow travel time at the edge level.
Total travel time, total.
Sorry, no, so it was a question as to whether, as an alternative to CVAR, whether you could do that and what the trade-off would be. Because I understand why you're doing CVAR. It's to only penalize places that have congestion. So if you were to instead have an alternative objective function where you penalize the difference between the no congestion travel time and the congestion travel time, the travel time in the solution, would that give you a similar solution?
Well, the point here is that we just focus on the congested arcs, right? And here we take the travel time on the congested arcs, and we ignore all the rest. It doesn't matter. So it is to say if you have all the arcs, right, and you have a couple of arcs where you have congestion, you should just minimize the congestion there, which means that you may spread the traffic around to reduce the travel time there on the congested arcs. But in any case, the objective function is the travel time on the congested arcs. I don't know if I'm answering the question.
I think I'll ask you offline. Yeah.
Okay.
I understand what you're saying. Thank you. Yeah. Thank you.
Okay. Right. So here there is a further step, because in the models that I have just presented, and also in the model that Jan et al. Presented in 2005, the paths, the eligible paths, are not the creation of the paths is not embedded in the model. So the paths are generated sort of a priori, offline, and then they are used in the model, and the traffic is assigned. And the real inconvenience is calculated ex post, because there is no way to do differently if you generate the paths outside of the model. And so it may happen that some paths that you consider as eligible, in fact, ex post turned out to be more inconvenient because of the traffic assigned on the paths, and also some good paths could be missed. So what we did was to build a model that embeds the path generation, so here we minimize the total travel time. We are back to the old objective function as a piecewise approximation, and we include in the model the generation of the paths. When we include in the model the generation of the paths, we have to impose that the path that we consider does not exceed the shortest path length by more than a given percentage. And the point is whether we do that for all the paths, with respect to all the paths possibly unused, or only with respect to the used paths. And we tried both, and we compared. And in this case, we pay a price, which is the fact that the model becomes a mixed integer program. We have binary variables. This is the total travel time, linearized. This is the limited inconvenience with respect to possibly unused paths. And these are the binary variables. For K is the path, and C is the OD pair. And if we consider a limited inconvenience with respect to the used path, then we have this change in these constraints. Right. So binary variables is not a good news. But again, we used a heuristic column generation scheme. They look all the same, these heuristics, because they're all based on the same idea. But depending on the model, the procedures to generate the new improving paths change also substantially.
Just a quick heads up on time, about 3 or 4 minutes left.
Yep. And again, here the quality of the heuristic is good. You see the gap, the maximum average and maximum errors are below 1%. Yeah, maximum sometimes 1%, 1.5%. And this is the result. So also in this case, we could solve the instances, the Sioux Falls, Chicago, Winnipeg, without computational problems. And again, we find similar results that we are between the user equilibrium and the system optimum, and we get close to the system optimum, depending on the network. If you have a heavy traffic, it takes longer. You have, sorry, not it takes longer. You need a higher value of the inconvenience to reach the system optimum total travel time. So of course, the results depend very much on the network and on the traffic that you have on the network. So how to distribute vehicles over the different paths? This is an open question. Should we give incentives? Also, it would be interesting to consider the time when the vehicles leave from the origin. The problem should have a dynamic nature, decentralized optimization. So there are many open questions that should be answered. Thank you very much.